For the second problem, okay, we have x is equal to the square root of y, x is equal to 2, and we have y is equal to 0. Now, there are various ways that you can work out the area as well as the volumes. And we have, okay, at least with the figures. So you have a bit of a triangular section. Okay, so you have x is equal to 2. We have y is equal to 0. And we have x is equal to the square root of y. Okay, and that could also be written in terms of y is equal to x squared. Okay. Now for the points of interest. So you have a 2, 4, 2, 0, and the origin. And so you can look at the area in either of two ways. And if I were to integrate with respect to y, so you would take what we have here, looking at it from a width perspective, and integrating with respect to y. So I can go from y is equal to 0 to y is equal to 4. And you have the right-hand function minus the left-hand function. So we have 2 minus the square root of y dy. And square root of y is going to be y to the 1/2. And if I take the antiderivatives, so I have 2y, and the antiderivative of y to the 1/2 is going to be 2/3 of y to the 3/2. And this will be as y goes from 0 to 4. And in this particular case, right, 2 times 4 is 8. And we're going to have minus 16/3. And regardless of which approach you take, okay, now we have for the area, this will be 8/3 square units. And let me mention now, if I were to integrate with respect to x, so I'd be going from x is equal to 0 to x is equal to 2. And we have the upper function minus the lower function. And if I were to integrate with respect to x, so I have x squared at the top, 0 at the bottom. So this will lead to just integrating over x squared dx. And the antiderivative, okay, so we have x to the third over 3 as x goes from 0 to 2. And notice, okay, the area still comes out to 8/3. And whichever technique you go with, whether it's integrating with respect to x or integrating with respect to y, okay, will still come out to the very same result. Now, if I'm looking at generating the volume of the solid about the x-axis, so we have at least for here, okay, now we have contact with the x-axis throughout, okay, for the base of this triangle. So I am enabled, okay, to use the method of disks. And in the case of the method of disks, okay, so we have for the radius, again, that's going to be the height. So again, we have x squared above 0. So you have x squared at the top, 0 at the bottom. That was the height, and that's going to be the radius, at least in terms of what we have, putting in the context of working with disks. Okay, so we have working with disks. So we have for the volume generated about the x-axis. Okay, so I'm going from x is equal to 0 to x is equal to 2. And we have pi times the square of the radius. Radius we have in square terms, and squaring even further, we're looking at pi times, okay, the fourth order of x. And so we have in the follow through, okay, so we have pi times x to the 5th over 5 as x goes from 0 to 2. And 2 to the 5th is going to be at 32. And So we have, in this particular case, we end up with 32/5 of pi. Okay, now, in the case of what we have regarding determination of the volume generated about the y-axis. Okay, and so in this one, I would say definitely the more user-friendly route would be to go with the method of shells. All right, and so we have this layout, okay, again, so we can take y is equal to x squared, y is equal to 0, and again we have generating about the y-axis. And so in the case of what we have in the setup, and again, so just taking what I have here, so for the projected radius, again, that is going to be at x, and in the case of the height, so you have h of x, that's going to be at x squared. So for the volume of the solid generated about the y-axis, and again, if I were to go with the method of shells, okay, I would still preserve integrating with respect to x, and in this particular case, again, so I'm going from x is equal to 0, okay, to x is equal to 2. So I have 2 pi, p of x is at x, and h of x is going to be at x squared. And in the follow through, okay, so I have integrating from 0 to 2, multiplying out, so I have 2 pi x cubed dx. And we have for the antiderivative, so we're going to have pi times x to the 4th over 2 as x goes from 0 to 2. Okay. And so just taking what we have here, so we have 2 to the 4th is 16 divided by 2. And so for the volume of the solid generated about the y-axis, okay, this will come out to 8 pi cubic units, whereas again, what we had generated about the x-axis, this turned out to be 32/5 pi cubic units.